Hi class, this is the video solution set to academic conference for the week 4. It's about confidence intervals, in particular confidence interval for a proportion. And so I showed a graph of the Gallup polling results, and I wanted you to look specifically at the most recent statistic, which is the statistic of 0.48. And that's the proportion of the respondents that were asked the question, do they approve of Obama's performance? That's 48% said that they did. Now, so the question's binary. So this is a binomial distribution. However, when we have enough people answering this question, or the sample size is big enough, we can approximate the binomial distribution as normal. All right, this certainly satisfies those conditions, and so we are okay to assume that this is going to follow a z distribution in terms of the sample proportion. So it says the true proportion of all voters is likely close to this 0.48 number, but probably different since we didn't ask the entire population of adult Americans, only 3,600 of them. So we need a confidence interval. We know that our estimate is not exact, so we want to interpret it relative to some sort of level of confidence. And we're going to construct a 95% confidence interval, which is very common, the most common. And I'm asking for the upper and lower limit. So what's the upper bound or lower bound? And the formula is going to be, well, my sample proportion, which I believe your book uses p hat, other textbooks use p bar or just p. The sample proportion plus and minus, plus for the upper limit, minus for the lower limit, a standardized value, this is called the z critical value, times the square root of the population proportion minus times 1 minus the population proportion over the sample size. And what we plug in here, all right, is based on our sample results. So we had 48% or 0.48, and 1 minus that would be 0.52. So your textbook gives a formula where this is appropriate, and I see that many of the groups actually use this, and that's fine. Another way that you could go about doing this, and probably a polling institute like Gallup does, is regardless of what you get for a sample proportion. We got 0.48, but if we got 0.2, 0.1, regardless of that, plug in 0.5 for p. And the reason is a value for 0.5 for p will give you the largest possible numerator in this fraction. And the largest possible numerator in this fraction will make for the most conservative interval. So to do this in the most conservative way, regardless of what you get for p, plug in 0.5. I'm going to calculate it this way because the textbook has it this way. But of course, if we plugged in 0.5, since our sample proportion is so close, it's not going to matter in a significant way anyway. That's our sample size. And the z for a 95% confidence interval is 1.96. My sample proportion, of course, is 0.48. Now, this term to the right-hand side, or the term that I'm adding and subtracting from my sample proportion, is called the margin of error. If you look closely at most polling results, they'll report this. And the audience or the reader can simply add that number to the sample statistic and get the upper limit, or subtract it to get the lower limit. So let me go ahead and calculate that margin of error. So 0.48 times 0.52 divided by 3,632. Take the square root of that, multiply it by 1.96, 0.0162, let's say. So the upper limit is 0.48 plus the margin of error. .4962. and the lower 0.48 minus the margin of error. .4638. Interpreting this, I'm saying that I'm 95% confident. I'm 95% confident that the true proportion of Americans that approve of Obama's performance is between 46.38% and 49.62%. All right, we're 95% confident that the true proportion, P, is between these two values. Now, if a researcher like Gallup wanted to decrease this level, okay, what options are available? Well, one option that we typically don't want to use is reducing Z. And so, how do I reduce Z? Well, if I lower my confidence from, let's say, 95 to 90, then my Z goes from 1.96 to 1.645. So, holding everything else the same, if my margin of error decreases, which will happen from a lower level of confidence, then my confidence interval becomes more narrow. All right, or decrease the width. Now, the problem is that, of course, I can keep doing this, and I could report a 20% confidence interval that's pretty narrow. But I'm only 20% confident that my range of values contains the true value. And so we typically stay around 95%. The lowest level is usually 90, the highest 99. And the real tool that we have as statisticians to decrease the width is to increase N, increase the sample size. More often than not, the remedy to any statistical problem is increasing sample size. As N approaches capital N, as little n approaches capital N, your interval is going to get tighter and tighter around the truth, right? So this is what we prefer. Of course, this is a possibility. So let's say Gallup wanted to report the 95% confidence interval, but wanted to have the margin of error of no more than 1%. All right. So the margin of error is going to equal 0.01. And I want to do a 95% confidence interval. So Z is going to equal 1.96. And the question is, well, how large does my sample have to be? Or what's the smallest sample I could possibly take and get this margin of error to stay at 0.01%. Now, my formula for the margin of error is the Z times this value. So this has to be 0.01. We know that this is 1.96. This is what we're after. And I just told you that the most conservative thing to do is to plug in 0.5 here. So given this equation, we see that if I can solve for n, I could get my answer. So we've got to rearrange terms. So toward rearranging these terms, if I left z on this side, probably the easiest way is leave the square root term on the left side. We'll keep the value for the margin of error at 0.01. And then, so this is that expression. I can remove the square root by squaring both sides. And then, since my expression here in parentheses is 1 minus p times 1 minus p over n, I can finally get n separated here, which would be z squared times p 1 minus p all over 0.1 squared. Right? And if you plug in these values, 1.96, 5, you're going to get 9,604. So n needs to be greater than or equal to 9,604. So I'm just rearranging the margin of error term and solving for n. Hopefully that helps.